Welcome to Physics with Mateu and Julian. Today, we are going to be measuring the surface temperature of the sun using various household objects and principles from blackbody radiation. More specifically, we're going to start off by using equations as given to us by Max Planck, describing what the blackbody spectrum is and how we can calculate it. From there, we're going to gather data using a homemade spectroscope to measure the wavelength of light coming off the surface of the sun. And then from there, we are going to use mathematical principles to derive an expression for the temperature of the surface of the sun, combining everything together.
Well, what is a blackbody? A blackbody is an ideal object which perfectly absorbs and emits all frequencies of light on the electromagnetic spectrum. The sun is a pretty good approximation of one.
Mateo, what is an ideal object?
Oh, sure. An ideal object is just a theoretical model for intents and purposes of an experiment. Realistically speaking, no object is going to be a perfect blackbody, but we can't assume it is so and get a very good approximation for our experiment.
What makes a blackbody special is that the energy emitted per unit area per unit time for a small range of frequencies, a quantity referred to as the spectral energy density, turns out to be a function of the surface temperature of the blackbody and the frequency of light. Physicists for a long time were unable to model this relationship mathematically, a struggle known as the ultraviolet catastrophe, which ended with the equation given by Max Planck. This equation describes a blackbody radiation spectrum with a specific light frequency at which spectral energy density is maximized.
For our intents and purposes, measuring the wavelength of light is much more feasible than measuring its frequency. So we need to switch this equation to be in terms of wavelength. We can begin with the equation relating frequency to wavelength. Frequency equaling the speed of light, c, divided by lambda wavelength. By differentiating this equation, we now have an expression for frequency and for df in terms of wavelength and d lambda. Combining these terms together into our previous equation, we get the following expression for spectral energy density in terms of wavelength. If we wanted to mathematically find the wavelength with the peak energy density, we would simply take the derivative of our function here and set it to 0, as we learned to do in calculus. Another way to do this, however, is to draw a relationship using a computer model of this curve, where we derive something called Wien's displacement law.
Mateo, what the hell is the relationship between Planck's law and that weird curve?
Oh yeah, so basically the curve represents how spectral energy density changes with respect to frequency, and the equation tells us how a small change in frequency will affect a change in the spectral energy density. So it's kind of like the slope of the curve. So to actually calculate the surface temperature of the sun, we will use an expression called Wien's law, which describes the relationship between the surface temperature and the wavelength of highest spectral energy density for a blackbody radiation spectrum.
Dude, I'm still confused. Is that Wien's law?
No, Eamon. That's Planck's law. It tells us how to plot the curve that describes the spectral energy density. What Wien's law tells us is how the peak of that curve changes depending on what the surface temperature of the object actually is.
It's possible to construct it by differentiating this expression and setting it equal to 0 to find the local maximum. However, it's much simpler to infer Wien's law using a blackbody spectrum simulation. Because we started on the backs of centuries of physics, we can begin with the power rule form of Wien's law. Because there are two unknowns, alpha and b, we need two wavelength temperature pairs to build and solve a system of equations for alpha and b. To do this, we will use our PHET, University of Colorado, Boulder simulation, with our first temperature wavelength pair being 5,800 Kelvin and 500 nanometers, and our second pair being 11,000 Kelvin, 263 nanometers. Here we have our two coordinate pairs of temperature and peak wavelength, and here we enter them into a system of equations using the power law for Wien's law. Here we solve the system of equations for alpha and b, first dividing the two equations to eliminate b and solve for alpha, which we calculate as -1, then plugging -1 into one of the equations to solve for b, which we approximate at 0.0029. Thus, we have established Wien's law as temperature equals 0.0029 divided by the maximum wavelength.
To perform this experiment, we use a device called a spectroscope, which separates light into a spectrum, allowing for analysis of that spectrum to extract information about the light source. We crafted the spectroscope using cardstock and sliced from a CD, and instructions from the YouTube channel IUCAA SciPop. When light from the sun shines through this slit in the front, the light reflects off of the CD. The reflection of the CD will spread the light into its various wavelength components, much like a prism, and the slit in the back allows us to peer into the device to view the distribution without any outside light interference. In order to collect data for later analysis, we use a standard phone camera to capture the reflected light off of the CD.
Artlist.io.
Now that we have our photo of the sun's wavelength distribution, we're going to go through the following process to turn it into surface temperature. We're going to start with our photo. We're going to put it into a color intensity meter that will tell us how intense the color of any particular point in the image is. We're going to find the point on the image with the highest intensity, and we're going to take that color and turn it into a hex code, which is just a computer definition of a color. Then we're going to take that hex code and we're going to convert it into a wavelength of light. And we're going to take that wavelength of light, we're going to plug it into Wien's law, and we're going to output surface temperature of the sun. Okay, now that we've taken our photo using the spectroscope, we need to isolate the region of the photo with the scattered light radiated from the sun. So we can tell this is the top section because it has the clearest wavelength band, whereas the bottom section is just distorted light in the lens of the camera. Now we take the photo and upload it into a website created by senior LIDO scientist Changjiang Yang, which outputs the color intensity of the photo at a given point in terms of blue, green, and red. After sampling points across the image, we isolated the maximum intensity pixel to be in the turquoise blue band, straddling the blue and green zones. It had a maximum intensity in terms of blue and green, and therefore had the greatest sum intensity of all points in the photo.
We then took the photo and used a tool called the image color picker to find the point's color represented as a hex code. Finally, another online tool called 405nm.com helped us convert the hex code into the nearest wavelength approximation on the visible light spectrum, which output a 98% match for 489 nanometer light wavelength. With this value for the wavelength of light at which the sun's spectral energy density is maximized, we used Wien's law to solve for the temperature of the surface of the sun, which we calculated as 5,930 degrees Kelvin.
All right, now that we have our value for the surface temperature of the sun, we can just quickly evaluate how good of an approximation it is using the formula for percent error, which takes the absolute value of the difference of the value we measured minus the value we expected, divided by the value we expected, times 100%.
Our measurements gave us some pretty good results. As Vet told us, our measurement should be around 5,800 degrees Kelvin. Our actual measure results using our household items was 5,930 Kelvin. Plugging into the formula, that gave us a 2.2% error.
2.2% is quite low. So this is a great experiment where we can apply some basic physics principles and use some just common materials to learn more about the world around us.
Artlist.io.